Okay, welcome. Today's lesson is on field effect transistors, lesson 17 for Mechatronics. First, I want to do a little bit of review about transistors in general. Remember, these are called bipolar junction transistors. We have a base, a collector, and an emitter. And current generally flows through from the collector to the emitter, and the base current controls how the transistor operates. Remember, we had these three operating regions. We have cutoff region where nothing's happening. We have this active region in green where the transistor is acting like an amplifier. And we have the saturation region where we want to operate and the transistor is acting like a switch. And we talked about ways that we can build a circuit to ensure that the transistor is properly forward biased so that it is behaving like a switch. That's what's shown on this slide. Remember, this reviews how we get the circuit into saturation region. We start by, usually you're given some load that you're trying to switch on or off. You should know what the current is that that load requires. So given that current, you can calculate what the collector circuit resistor should be. And in order to do that, we need to make an assumption about the voltage drop VCE. We assume it's 0.2 volts. Given that, we make an assumption about the gain, that it's 10, which it should be if it's in the saturation region where these lines are smushed together here. That tells us what the current IB should be. Then, if we know what the desired IB current is, we can calculate the RB resistor using Ohm's law and the given base current. Okay, then we briefly talked about some ways transistors are used. Up here, remember we generally used them like this as a switch. These are different examples of how they're used as a switch. This is a small signal amplifier. I described that briefly in class. And then we talked about a Darlington pair, which is used to increase current by cascading them together. And there's a good example in the book that describes this type of a circuit. It's actually in section 10.6, if you'd like to see an example like that where they amplify current. Here's another example we haven't talked about yet, but it's very common. You probably heard of this, a phototransistor. And so imagine you had N, P, and N BJT, bipolar junction transistor, and you had it connected in a circuit where it could conduct. Now, what I've drawn here, normally, if this were a BJT, there would need to have, you'd need to have a base connection here, because this would be the collector, this would be the emitter, this would be the base. But in the case of a phototransistor, it's actually light from the sun falls on the base, and that's what forward biases the transistor and allows it to operate. I said from the sun, it can be any light. So light that's basically photons, which don't have to be from the sun, but photons fall on the semiconducting material, and that's enough to forward bias it and get it to operate. Now that's using the photovoltaic effect, which is also how solar cells are working in a sense. And what interesting, it was Bell Labs that invented the transistor, and they also invented the first solar cells and many other things. They invented optical fibers, fiber optics. They did the first satellite communication satellite fiber optics. Okay, and I can tell you more about that in class. All right, so for today, we're introducing, let me shrink this a little bit, field effect transistors. And there's two basic types of field effect transistors. Mostly we're going to talk about MOSFETs, metal oxide semiconductor field effect transistors. So these are similar to the BJT bipolar junction transistors in the sense that they all have 3 leads. So they're a triode type of device. And we use them to turn things on and off as a switch. But they behave differently, and we'll talk about that here. So with a field effect transistor, instead of a base, a collector, and an emitter, we have a gate, a drain, and a source. And that's just because we have different types of physics going on here. With a FET is a voltage controlled device. So remember a BJT, how does this compare to a BJT? So think about that. So here we have a voltage controlled device where a small gate voltage controls a large drain current. So here is the gate right here, and this is going to be a voltage, not a current. And we're going to get current flow from drain to source. Okay, that's going to be our current. That's going to be the IDS, drain source current. So recall for a BJT, a current at the base, a base current controls the collector current. So this is a big difference. Now we have voltage can control current. Okay, so it also behaves like a small value resistor. The other thing is with a BJT, remember we have this, and we've got the base, and current flows from there's a base current that flows from the base into the emitter, and there's the collector current. With this, there is no current flow into the gate. There's just that voltage. Here's our, let's look at a hydraulic analogy here. I'll make this a little bit bigger. So imagine you had a pipe like this, and you had this contraption that had a little lever. So if you pushed on this lever, it would pull this L-shaped valve out of the way and would allow current to flow. If you don't apply any pressure there, this thing slams closed and it shuts off flow of fluid. So here we can see the pressure pushing on the gate is like a voltage, and that moves this out of the way and allows current to flow through. Okay, so that's essentially how this device operates. We need a large gate voltage in order to allow current flow. And in the next slide, I'll talk about the physics of kind of how that's working. Oops. I also want to point out a JFET. A JFET is a junction field effect transistor. And it operates, we're not going to get into the details of JFET, we won't use them, but imagine this is like the stepping on a hose. You've got, you would like current to be flowing from the drain to the source. By applying a voltage here, you are pinching off the hose and preventing current from flowing in the pipe. Okay, so that's how JFET works, but we're not going to go into too much detail on those. Okay, so back to the MOSFET. So again, considering this fluid flow analogy, if you push on the gate, it allows fluid to flow. And remember, we talked about this before, voltage is kind of like pressure, and current is kind of like fluid flow. So again, even this analogy works with voltage controlling a current. So zooming out here on our slide. So here's kind of the physics of how a MOSFET operates. When the device is set up, there's a P-type material, and this is an N-type enhancement mode MOSFET. That's what this is showing here. So you have a substrate material that's P-doped, and then you have these two channels that are N-doped. And when you make that, it creates a depletion region around these regions where these PN junctions are. As we apply in this scenario, even if you have a voltage, you've got a big voltage here, and this is ground. With no voltage at the gate, current can't flow because there's a depletion region here that prevents current from jumping across this depletion region. That's what I draw in there. As we apply a small amount of voltage, we push out this depletion region and start to create a channel wherein current can flow. And the more, boy, that is a terrible job of writing that. The more channel, the more we increase this gate voltage, the bigger this channel gets and more current can flow. So this would be plus volts here, and this would be ground here on this end, and current is flowing like this. And remember, electrons are going the other way. So current, we get current from drain to source. This is I ds, drain to source. Okay, next slide, we're going to look at kind of the characteristic curve of how this guy works. So again, this is an N-channel enhancement mode MOSFET. It is controlled by the gate to source voltage. So VGS, this is gate to source voltage. In order for this thing to work at all, so down here is the cutoff region. Now, similar to our BJT, we need our VGS to be greater than a threshold voltage. So this is the threshold voltage here. Typically, the threshold voltage is about 4.5 volts. I already have that on the slide right here. So that's quite a bit more than what we required for a BJT. So remember, a BJT was only about 0.6 or 0.7 volts to get current flowing through the base to turn the thing on. So you need more voltage here. And so once now, as we increase gate voltage, that's these horizontal lines here. So here's 4 volts, 6 volts, 8 volts, 10 volts. Now on these axes, we have VDS, which is the drain source voltage, right? So that's this here. This is how much voltage is being dropped in the device. And remember, just like the BJT, we usually want the voltage dropped in the device to be as low as possible. We don't want to be losing 14 volts in the MOSFET. We'd like to be much lower than that. Okay, so that gives us a hint. We probably want to be way to the left, and we do. So as we increase the gate to source voltage, we will get more current flow, ID, through the device. And that's good. We usually want current going through the device so we can turn on our device. But if we want to reduce the amount of power loss in the device, we want to be to the left so that we're not burning up energy in the MOSFET. So in this case, we want to be in the linear region, not the saturation region, which is a little bit confusing. When we meet in class in person, I'll go over some of these videos and show kind of the physics of how these things work. But you basically have this interesting interplay between the gate and source voltage that turn the device on and the drain to source voltage. So that's why you get this interesting behavior. But for our purposes, we want to have the voltage at the gate to be above the threshold voltage so that we turn the device on. And then we have current going through some load that's, probably up here. And, it's a light or a motor or something like that, and we're switching it on. Okay. MOSFETs are used for digital logic, which is the next block of material we're going to talk about after the GR. And for those, they're typically turned on with about 4.5 volts. So here we'll look at a quick slide of how this might be used in a circuit. In this example, this might be a microcontroller. And we're wanting to switch on a larger device. So maybe this is a motor or an actuator of some type. Maybe it's a relay to turn on pneumatic pressure for an actuator or something like that. So here's our MOSFET. So this is the gate, this is the drain, and this is the source down here. And so you're thinking about what's it sourcing? Well, it's sourcing electrons. So electrons be flowing up that way. So here, let's think about how this works. If this is a standard NPN BJT over here, so this is the base, the collector, and the emitter. when we turn this on and current flows, we have voltage flowing from the 10-volt source through the resistor and through the transistor. This is ground. What would the voltage be right here? Well, that's the voltage at point C. Well, if this is saturated and the standard saturation voltage drop for a BJT is 0.2 volts, then that means this is 0.2 volts. If this is 0.2 volts, that means this gate is 0.2 volts. Is that MOSFET on or off? Well, it's below the threshold voltage, so this is going to be an off situation. Okay. Now, if the transistor here is not turned on, current is not flowing, we have no current flow, it's like this part of the circuit is not even here, and there's no current flowing through the resistor. That means here at the gate voltage is going to be the 10 volts that's up here, because there's no voltage dropping through the resistor. So if that's the gate voltage, then the gate to source voltage is 10 volts, and this would be on, be the on configuration. Okay. All right, so finally, to sum up here, let's talk about pros and cons between a BJT and a MOSFET. So again, bipolar junction transistor, metal oxide semiconductor field effect transistor. All right, so as I mentioned at the start here, a BJT is a current controlled device and a MOSFET is a voltage controlled device. So that right there might dictate which one you pick for a given design challenge. Now, in general, a BJT requires less voltage. So remember, we only need about 0.7 volts to get it forward biased. Some micros are only operate on 3 volts. So if you're using one of those devices, you would not be able to use a MOSFET unless you did some other scheme to amplify the voltage. So whereas a MOSFET requires greater than 4.5 volts from gate to source to turn it on. Now, a major drawback of a MOSFET, or another drawback, is that it can only switch on the order of 50 to a few hundred volts, whereas a BJT can usually do thousands of volts. So if you need to do a super high voltage source, you're going to use a BJT and not a MOSFET. Now, a drawback of a BJT is it requires current. So remember, I mentioned that you've got your BJT circuit. This is the base. Current flows through the base, and that you got to have a steady flow of current to keep that thing on. A MOSFET, it doesn't have that need. So it's just got as long as you've got a positive voltage here, there's no actual current flow into the device. So that's really nice. So the other thing about BJT, it's got a fixed voltage drop, and that's usually, through here, it's a VCE of 0.2. A MOSFET has a voltage drop, but it's much lower. VDS is usually about 10 times less than a BJT, and it consumes about 10 times less power too. So it's more efficient. It's not going to burn up as much energy in your device. Another problem with the BJT is that you have to have a resistor here at the base to control base current flow. MOSFET doesn't require that. You can hook up this MOSFET directly to the output pin of your microcontroller and turn it on and off just like that. Okay, so that means it's got a simpler circuit, easier to miniaturize, easier to prototype. MOSFETs are more expensive, BJTs are less expensive. Okay, in class, I'll go over some of these videos and we'll talk about kind of the physics behind them and how you might use them. And then we will talk about the GR, which is coming up. So that will be next lesson. So I will review the GR a little bit and talk about what the format of the GR will be. All right, thank you for listening.